Okay, in lesson two, we're going to be looking at radical functions, but if you weren't having just an x under the root sign. So our transformations work for all the simple ways you can manipulate root of x. You can multiply it, you can add it, but what if it's more complicated than just a root x under there? So in that case, we're going to treat the thing under it like it's its own function, and then we're going to see what happens when you take the root of that function. There's a really long discovery at the beginning of this lesson, and I kind of want to skim through it because it's not actually the best, but it's all pointing to a couple rules that we'll get to at the very end. So we're going to do just 4 of these. There's some questions at the beginning. They probably, no, I think you don't even have those on your sheet anyway. So this is a graphing question. Plug these into your graphing calculator and show what it looks like. So if you have your original function was x squared, and now you take the root of x squared. Well, that actually is just going to equal absolute value x. So it's going to come up kind of in a straight line, and come up kind of in a straight line. So it ends up looking like that. Domain of this one is all numbers. This one is actually fine. You can have every single number has a point on this graph. The range, actually I don't know what these are. These aren't for this function. The range of this one, so domain, all x, range, all y greater than or equal to 0. I'm just doing it in shorthand to be kind of quick. Oh, this is, oh, they wanted to do it 2 different ways. They wanted to do the domain and range of the original function and the domain and range of the root. But this is actually true for both of them. For both of them, it's all x for the domain, and it's bigger than or equal to 0 for the range. Okay, let's try that again with this one. This is really going to start pointing to what we're trying to learn from this lesson. If you plug this into the graphing calculator, what is the square root of x plus 1? You end up getting something like this. So domain and range of the original function, we should be able to do just fine. It's all x and all y. Domain is x is a member of the real numbers, and x, that's it. It's just all real numbers. And range, y is a member of all real numbers. Domain and range of our root, the domain. X is a real number, so long as x is bigger than or equal to, what's the x-intercept here? That should be -1. Bigger than or equal to -1 in this case. The range of our root function is the usual greater than or equal to 0. So y is a real number so long as y is greater than or equal to 0. In that one, I'm skipping 2. I don't think we need to do all these to get the idea of what's going on. 4. If you have the absolute value function, this is actually going to be a little bit tricky to graph. There is a button for it, I believe, on your graphing calculator. You might have to search for it a little bit, or it might even be in the math button. But anyway, try and find the absolute value button for it, and try and graph the square root of the absolute value of x. You should get something like this. If you can't find it, you could always go onto Desmos and do it with Desmos. I'm pretty sure Desmos has it. Let me just double check that. Yep, Desmos has that button. So if you can't find it on your graphing calculator, you could always do it with Desmos. So what's going on in this one? Well, the domain is all real numbers. I'm just going to talk about it. The original function, the domain, was all real numbers. Our root of it is still all real numbers. The range of the original function was greater than or equal to 0. The range of the new function is greater than or equal to 0. But that's a little bit less interesting than what we're trying to focus on. One of the things that we actually really care about in this lesson is where do they touch? We kind of end up with these 3 points. These are going to be our invariant points. That's going to be one of the big things that we're going to be learning in this one. And the invariant points are going to be everywhere where there's an x-intercept on the original function, because that means it has a value of 0, And when you take the square root of 0, it's still 0. So 0 doesn't change, and as we talked about in the last lesson, 1 also will not change. So it's going to always hover between the 0 and the 1. Those are going to be fixed, but then it's always going to be kind of concave down if it's coming from a line. Could do different things if it's not. Actually, let's look at 5 really quick as well. If I'm looking at this one, and I start to graph it, it's going to go like this. Something up like that. It starts where the x-intercept is, and everything that's in the negative does not exist in my new function. That's another one of our really important points that we want to recognize. And we kind of saw that in this one as well. It started where the x-intercept was, and the negative part does not exist. Because you cannot take the square root of a negative number, we're now restricting the domain. We're cutting that part of the graph off. And with this one, if you try and graph this, you're going to get nothing. The square root of negative x squared minus 1, there will be nothing showing. There is no numbers that are allowed to be. No x values can be subbed into this. They will all break the function. So this one does not exist. It's just a big blank graph. Okay. So repeat this for these following functions. So getting a little bit more complicated now. If you had this function, so plug in the square root of it, x squared plus 4, you're going to end up with, it's like you take the y value and you take the square root of it every time. So this looks like it's up at positive 4, so it ends up going down to 2. And actually square roots kind of slowly goes up from there. So it flattens the whole thing out. I'm going to skip domain and range. I think we're okay with that. If you need some more touching up on that, come talk to me once the lesson's over, and I can go over those with you. But this is domain is all real numbers, range is 2 or greater. In this one, so everything in this middle part between there and there, that part does not exist in our new graph because it's all negative. So this one's actually going to be a pair. It's going to be one thing sticking out that way and one thing sticking out that way. This is, I shouldn't have gone down. It stays going up, even though it gets flatter and flatter. Something like that. Invariant points again, the x-intercepts are going to be the exact same, and wherever the height of 1 was is going to be the exact same. And that's the things we want to learn about this. So, answer the following questions based on your observations in 1 and 2. It took 8 minutes, not too bad. In which of these examples are the domain and the range the same? Well, let's look back at this guy. In which of these are going to have the same domain and range? Well, that's going to be number 1. Not in this one, not in this one. In number 4. Not in this one, and not in this one. Only 1 and 4, and this guy too. 5, 6, 7. Should be capitals. And not in this one. So there's only 3 functions that have the same domain and range, which is all real numbers. What do these things have in common? All values of f of x, the thing under the root, are positive. And that's really just wanting you to recognize that you cannot have any, if you wanted to look at it really quickly, everything that falls beneath the x-axis is going to disappear. That's just what they want you to see. You cannot take the square root of any of these negative numbers. Same thing with this guy right here. All these negative values over here, they're not going to exist in our new graph. It's going to start at the x-intercept and go across. Okay. Bunch of things here. I actually like this little question. Maybe you try and do the C part on your own. Pause the video. Take 2 minutes. See if you can answer these. Select an answer. Okay. The graph of the root of a function of x does not exist not when the x value is negative. So this is actually a really important thing to recognize. You can sub in negative x values, you just can't have the entire value of the f of x. The whole function under the root cannot be negative. A lot of people actually make that mistake. They always assume you can't have a negative x. You can have a negative x if it's like root of x plus 5. I could sub in negative 3 here just fine. I could sub in negative 4 here just fine. I can't sub in negative 6. So the only rule is that the whole thing can't be negative. If f of x is equal to 0, the graph of the root of it lies on the graph of the original one. This is basically saying it's an invariant point. It's the exact same point. If the original function was 0, the root of it is also going to be 0. If f of x is between 0 and 1, we didn't talk about this. So if you have values of between 0 and 1, and you square root them, that actually makes them bigger. They actually grow. That's why in, where is it, this function right here, until we hit the point 1, which I'm calling like here, it actually was bigger than it. It started above the curve until you get to 1, and then it goes under the curve. So values between 0 and 1 become bigger. The value of 1 is the same, an invariant point. It's the exact same value, because square root of 1 is always equal to 1. And values bigger than 1 become smaller. Okay. Using all that, can we do a more complicated question? Oh, there's something else. I'm missing this sheet. This is just a nice little summary of what we're doing. I think we can go over this pretty quick. So if you had this straight line was your original function, like x plus 1, we saw this on one of our graphs. The root of it can have invariant point, and it's going to go above and then below. Same thing with absolute value of x, invariant points at 0 and 1, and then it goes above to below and above to below. So often in our questions, we're going to deal with straight lines. And if you take the square root of them, they always follow this pattern. So you should be comfortable with that. And once again, just the rules. So this is basically everything we just talked about. If f of x is less than 0, it does not exist. This is just a summary of what we did. So I think I'm going to skip this. These are all just those points I just discussed. You could read them. I don't think there's anything. No, this is all just what we just discussed. Okay, so let's try a more complicated example. Sketch the graph of y equals root of f of x on this grid. And then state the domain of it, of the original function and the new function, and state the range of the original function and the new function. Okay, this is fun. Looks complicated. It scared me the first time I looked at this, but it's not too bad. First thing, let's point all the invariant points out. So x-intercept, invariant. Invariant, invariant. Anywhere where it goes through a value of 1. So now look at the y value of 1. Everything that touches that is invariant. Okay. Everything that's beneath this line doesn't exist, so we don't have to worry about those guys. What about, we have a nice flat value up here. We probably want to look at these values and see where they go to. So this, from here to here, it's a value of 4. When you take the square root of it, it's going to go down to 2. So that's actually going to go to there and to there. Then we have the whole line, then we have the whole line, then we have the whole line. So we've got the flat bits done. We have the invariant points done. Now we just basically have to connect our dots. So it goes up, then over, and then straight across to flat. Okay, and then down and over. So I'm going to turn it sideways so I can do this bit better. Up and over. And down and over. So it should look something like that. Probably could have pointed this one out. This was at a height of 2, so it goes to root of 2. It's not a great number, but you could have marked that number off as well if you wanted to know where the peak was. But something like that, anything like that is good. If I were marking this on the test, I'd want to see that you did the invariant points. I'd want to see maybe that you noticed where the flat line was going. And as far as the curve goes, I'd want to see that it started above the line and then went beneath. Started beneath, then went above a little bit. Above to beneath. We're looking for that kind of thing. Domain of the original function. Well, we have arrows. So the domain of the original function is all real numbers. That's what those arrows mean. They go forever. Let's go to range of the original function. So it goes down forever, but it has a max height of 4. So range is real numbers so long as the height is less than or equal to 4. Good. Okay, domain of the new function. Well, we have a very clear start and a very clear end. So the domain is real numbers so long as, there's actually a lot of people that switch the order of these two things. I don't care either way. It goes from -1 to 3 all the way up to 16. X in the middle, and it goes between those numbers, and it can equal those numbers. Those numbers are permitted. Range of this function, it's only between 0 and 2. Zero, 2, it's between them, and it can equal them. Yeah, that's it for that one. Example 2. In each case, the graph g of x is shown. Determine the domain and range of h of x without sketching it. So without using Desmos, let's just look at this and see if we can tell what the domain and what the range is going to be. Of if we took, yeah, h is the square root of it. So if we took the square root of this thing, the domain would be everything except for where it's under the x-axis, which is nice. It's everything. The range of it is going to be, if you take the square roots of these values, it's going to go infinitely high. The square root of infinitely high is still infinitely high, so it's going to go up forever. But it has a bottom of 3 right now. If you take the square root of that, it should have a bottom of root 3. So y is a real number, so long as y is bigger than or equal to root of 3. Not too bad. This one's a bit harder. So this is a cutoff point, this is a cutoff point, and this is a cutoff point. So none of this exists, and none of this exists in our new function. So the new function, x is a real number, so long as x is less than -2, less than or equal to -2, and we do a comma if we have two different parts to it, little comma, and x is between 3 and 8. So x is either less than -2 or between 3 and 8 are the only good things. Range. So we're cutting off all that. So it's going to start at 0, and it actually has a max height of 9. There's a point here, no arrow. So this is the absolute top of it. So y is a real number, and the height values can be between 0 and now the square root of 9, which is 3. So we can do it without even Desmos sketching it, or trying to calculate it by hand or with algebra or anything like that. Not too bad. Okay, let's keep moving so we can finish this. Actually, was that the last question? That was indeed the last question. So that's lesson 1 and 2, 20 minutes each. So you should still have a decent amount of time for homework. I think I'm free in the classroom now, so if you have questions, let me know. But not too bad of lessons, these ones. You just have to be careful. They really, really want you to be very familiar with the restrictions on root values. You know that you can never sub in a -1, and you know what the general idea of the curve looks like. As long as you have all that in your head, then you should be pretty good with these questions.